Hi class, this is the class video for Tuesday, October 27th. So homework for today, we are not doing the gases FRQs, so take that off for homework. We didn't get as far as I had hoped, but that's okay. You should watch the AP Classroom daily videos for 3.9 and complete the pre-lab for lab 3. That's up on Google Classroom. Also watch the AP Classroom videos for 3.5 and 3.6. Take notes, do the questions in the video, and we'll be doing a pair deck with questions on these topics on Thursday. So today's opener was when CO2 sublimates directly from solid to gas, what forces must be broken to separate the molecules? Well, that would be, since CO2 is a nonpolar molecule, CO2 is going to have only very weak London dispersion forces. So when CO2 is sublimating here, this is dry ice, we are breaking apart the weak London dispersion forces. So we went over one FRQ from last night, and let me go to that to go over that FRQ that we did in class. Number 1 in class today. So in 1A, they show you the boiling points, dipole moments, and polarizability of 3 hydrogen halides. So the boiling point, we notice as we go down here, is increasing. The dipole moment is decreasing. The dipole moment is related to the polarity of the molecule. The polarizability is increasing. And polarizability, again, is the squishiness of the electron cloud, how easily it can be distorted to create temporary dipoles. That relates directly to the LDFs in a molecule, the London dispersion forces. So whenever doing these IMF problems, what we first want to do before we tackle the problem, the question that they're asking, is to list the IMFs in each substance. So here we've got HCl, HBr, and HI. These are all polar molecules which have LDFs and dipole-dipole forces. So it's always good to list the IMFs as well as the polarity. I'll put that next to there too. So these are all polar. So if we take a look here, we've got to figure out whether it's the LDFs or the dipole-dipole forces that are causing this increased trend in the boiling point. So if the boiling point is increasing, we're saying that the intermolecular forces are increasing between molecules in these substances. But if you look here, the polarity is actually decreasing. So that's not accounting for the increased boiling point. It's the polarizability, which is increasing, that's increasing the strength of the LDFs and causing a higher boiling point. So here we can say that LDFs account for the increase in BP meaning boiling point, from HCl to HI. Polarizability is increases. That means we have increased LDFs, stronger LDFs, which in turn increases the boiling point. Now here, we definitely want to write in complete sentences and thoughts because, right, we want to use good writing and not just write, fragments. But so on an exam, you would definitely do that. But the idea is that the increased polarizability, the size of the electron cloud is increasing as we go from Cl to I here in these molecules. And so the LDFs increase due to the increased polarizability of the electron clouds, which in turn increases the boiling point. It makes it harder to separate these molecules as we get to HI. Okay, letter B, it says, based on the data in the table, a student predicts that the boiling point of HF should be 174, but the observed boiling point is 293. Explain the failure of the student's prediction in terms of types and strengths of intermolecular forces that exist among HF molecules. So again, here we're going to list the forces that are present in HF. So in HF, as with all molecules, we have LDFs. HF is polar, so it has dipole-dipole forces. But H also has Fon here. H is attached to F. So HF can also make hydrogen bonds with each other. So it has all three forces. Why is it that it does not have the boiling point predicted? These hydrogen bonds, okay, provide extra attraction. Okay, extra IMF, attractive force. I guess we should really call it an attractive force rather than IMFs. Provide extra force for between, sorry, not for, between the HF molecules. And so because of the hydrogen bonding ability, right, it's going to be harder to boil HF, harder to separate the HF molecules because they've got this extra hydrogen bonding capability here. Okay, part C, we are going to take HBr molecules in the liquid state and we're going to draw them as vaporized HBr. So I'll just draw that right here. So we have to completely separate the LDFs and the dipole-dipole forces that are holding the HBr molecules together into a liquid. And so we would get a gas afterwards, something like that. All right, part D, it says use appropriate chemical principles to account for each of the following observations. In each part, your response must include specific information about both substances. So here in part D, it says the melting point of NaF is 993, whereas the melting point of CSCl is 645. All right, so another thing you should always do besides listing the forces in this problem, and in all problem, we probably should have done it at the beginning too. We want to classify the type of substance for NaF and CSCl. NaF, we have a metal and non-metal. Okay, this is ionic. CSCl is also ionic. Oh, guess what? We're not going to use intermolecular forces to justify this response because we have ionic compounds. So now we're talking about the melting of these ionic compounds. We need to think about lattice energy, okay, and Coulomb's law. So here we can see that CSCl, CS and CS plus and Cl minus, these are larger ions than Na plus and F minus. This means larger ions means they are farther apart. Farther apart in distance. And so we now can invoke Coulomb's law. Okay, so Coulomb's law says if things are farther apart in distance, we have decreased force of attraction between the ions. All right, so then this explains why the melting point of NaF is higher than the melting point of CSCl, right? In CSCl, the ions are farther apart. This decreases the attractive force, okay, which then lowers the melting point. If you have less attractive force holding the ions together, right, your melting point is going to be lower because you have less force of attraction to overcome to separate the ions into liquid ions. All right, part E, we're going to talk more about this on Friday because this kind of deals with solubility and solutions. But again, here we're going to list, let's classify. Let's do this properly. Type of substance. For ammonia and pH 3, these are both molecular. Okay, so I know they're molecular. Therefore, I can go on to list my IMFs. Okay, so for ammonia, I'm going to be lazy and write all three. So LDFs, dipole-dipole, and hydrogen bonding capabilities. pH 3 is polar. Okay, so this is going to have LDFs as always, and dipole-dipole forces. So right away we see a difference in the intermolecular forces for NH3 and pH3. So now in solubility, we also have to look at the IMFs in water. Okay, so in water has LDFs, dipole-dipole forces, and hydrogen bonding. It can hydrogen bond with itself. All right, so we can say that ammonia is very soluble in water, right? Why? Because ammonia is able to hydrogen bond with water. It has similar IMFs to water. Remember the old saying, like dissolves like. So if we have similar intermolecular forces, then these molecules can basically substitute for each other, right, without any penalty or little penalty. So ammonia can hydrogen bond with water, and those water molecules can separate and hydrogen bond with the ammonia, and then you get mixing and dissolving occurring for the ammonia. Whereas pH 3, which is polar, right, it can still interact with water. Okay, but the forces that are going to mix water with pH 3 are going to be weaker forces. pH 3 can only form dipole-dipole interactions or dipole-dipole forces, and weak LDFs with water. Okay, so the more similar the forces, the IMFs between two substances, the more soluble they are, the more they will mix. Better mixing. So that was FRQ number 1. I'm going to post the answers to the other 2 FRQs. So please check your answers and let me know if you have any questions. So after we went over one of those FRQs, I asked people to review their IMFs. So this assignment is on Google Classroom. And so got a chance to go through this review activity. And it is a kind of an interactive card sorting activity. And it's on IMFs. There's a couple, directions here and also what to do. But basically, I'm going to run you through this. The first one is kind of a review. So if we take this molecule here, this is not trigonal, planar, not linear. This is trigonal pyramidal, 1 lone pair, 3 bonds. Here we have CO2, that's linear. Here is methanol, it's tetrahedral. SH2 is bent. BCl3 is trigonal planar. Here we have another trigonal pyramid, and here is another bent. So that's our sorting for that. The next part is to sort these into polar and nonpolar molecules. So that's polar, nonpolar, and polar. You should be very comfortable with classifying compounds as polar or nonpolar. And right, it's absolutely necessary to be able to say whether something is polar or nonpolar to draw a correct Lewis structure and to be able to classify it as the geometry and the polarity in order to talk about IMFs. Here, we're not going to put these into their IMF categories. So pH3 is polar, but it cannot hydrogen bond. H does not have Fon. Here, we only have a nonpolar CO2 molecule. It's only going to have dispersion forces. Methanol, well, this H has Fon. H is bonded to an O. It can hydrogen bond. SH2 is polar, but it cannot hydrogen bond. BCl3 is nonpolar. NH3, ammonia, hydrogen is attached to Fon, so it can hydrogen bond, and we already know that water can hydrogen bond. And just keep in mind, right, right here, for polar molecules that can't hydrogen bond, they also have LDFs. It's not that they don't. And hydrogen bonding molecules that can hydrogen bond also have dipole-dipole forces and LDFs. All right, then we had to rank in terms of lowest surface tension to highest surface tension. Here's the answer right here. Okay, and then there are 3 isomers of pentane here. We want to explain which intermolecular force plays the largest role in the boiling point. Well, these are all nonpolar. So if they're all nonpolar, then the only force that can play a role here is, you've got it, LDFs. Part B, which has the lowest boiling point? Well, we're going to look for the most compact molecule, the one with most branching, instead of a long, skinny, long thing that has a lot of surface area. So in this case, it's neopentane. For part C, highest boiling point, the longest, skinniest, and molecule with the most surface area, most contact area, that would be pentane. So those, once we have longer, straighter, more surface area molecules, that's going to increase the polarizability. So we could say longer, straighter, I'll just say longer, larger contact area molecules are more polarizable. which increases the strength of LDFs between molecules. Okay, and then vice versa, we could say for neopentane, more compact, more branched molecules are less polarizable, which decreases the strength of LDFs. So that's our isomers of pentane there. Now, if we take a look, we can order these things from lowest boiling point to highest. Again, we start with the lowest boiling points for things that just have LDFs. Here we now go into polar molecules that can't hydrogen bond. So this molecule is polar because of the Br here, but it cannot hydrogen bond. And then finally, we have two things that can hydrogen bond, but this last molecule, this is propanediol, it can actually hydrogen bond in two places, whereas this propanol can only hydrogen bond in this place. So that would be your answer. You should discuss that in your box. And then finally, this last question, this first one is kind of weird. It basically is looking at the density of PVC versus polypropylene. And since the density of PVC is higher than the density of polypropylene, you would say that the beads that sink are the PVC versus the polypropylene, which actually floats on the top. So the kind of the clue is that the spacing is the same in each polymer chain. Finally, for part B, you have to justify why these boiling points are different. Again, list the IMFs. So in the first, propene is nonpolar, so it only has LDFs. Vinyl chloride is polar, so has LDFs and dipole-dipole forces. Therefore, we would expect that propene's boiling point is lower because it has weaker intermolecular forces. It only has LDFs, whereas vinyl chloride has stronger IMFs because it includes LDFs and dipole-dipole forces, so its boiling point is higher. So that is the classwork that was a review for the quiz. And so then we went back after doing a review. We went to we took the quiz, and then we went to this Google Doc and asked people to draw various phase changes after we looked at a FET simulation. So you can take a look at the stock and look at the different phase changes. I'll put some comments on there. And so there are 11 different phase changes, I guess 12, including the first one. All right, so I'd like to also show you this. So 3.3 is about solids, liquids, and gases and their changes in state. So phase changes is the same terminology as the change in the state of matter. And the state of matter at a particular temperature depends on the strength of the particle attractions versus the amount of kinetic energy the particles have. One thing that you should kind of stick into your brain and make sure that it sticks is that the average kinetic energy of molecules is proportional to the Kelvin temperature, directly proportional. So depending on how much, depending on what the temperature is, that dictates how much average kinetic energy the molecules have. And depending on the strength of the intermolecular forces or the particle attractions, if the kinetic energy is larger than the amount of particle attraction, then those attractions will break and you will have a gas. If the kinetic energy at that temperature is not high enough to break those attractions, the substance will remain as a liquid or a solid. And we'll definitely look at this more. So how they look before and after a phase change, how a substance looks depends on the type of the substance. Okay, so remember we have our 4 different solids, our 4 different substances. They have different particle forces holding the particles together. So in this PhET simulation, maybe if we can get to the PhET simulation. So in this PhET simulation, we have, it shows states of matter. And so we took a look here. Here we have solid neon gas at 14 Kelvin. That's pretty darn cold. But you can see that even at this temperature that the atoms of neon are still wiggling a little bit. They still have some kinetic energy, some movement. Now, if we start to add heat to our solid, it starts loosening up those intermolecular forces, in this case, interatomic forces, which are just LDFs because it's just a single atom, and that's going to be nonpolar, and that's the only intermolecular force it has. And we don't have to apply a lot of heat to break this apart. In fact, at 28 Kelvin, the neon will change into a liquid. If we apply more heat, okay, and heat it further, we can change it into a gas at 56 Kelvin. And now we've completely broken apart the LDFs that were holding the neon together in a liquid and solid. So back to the liquid, we still have LDFs here, but they're loosened. Okay, there's enough kinetic energy that it's allowing for the atoms to slip around and move more randomly. Whereas here as a gas, we've completely broken apart those LDFs. We've broken the LDFs holding the atoms together. If we take a look at oxygen, we can solidify oxygen at 27 Kelvin. Still pretty cold. If we apply heat, we start loosening the LDFs. Remember, oxygen again is nonpolar, and so it's only held together with LDFs in the solid and liquid states. We loosen the LDFs. We cause the molecules to have enough kinetic energy that it can, break the LDFs temporarily and allow the molecules to slip around. And at 57 Kelvin, we now have a liquid. If we continue to heat, the molecules will gain more and more kinetic energy until they have enough energy to break the attractive LDFs, the attractive IMFs between the molecules. And at 113 Kelvin, we now have oxygen gas. The LDFs have been completely broken. There are no more intermolecular forces between the molecules, and the gas molecules are completely free from each other and separated. Finally, we have water here. Water and ice makes this beautiful hexagonal structure that partly explains the hexagonal structure of snowflakes, the hexagons that snowflakes make. So here, again, at 146 Kelvin, we have ice, a solid. If we start heating, we start breaking apart the IMFs. In water, of course, water is polar and can hydrogen bond. The IMFs that we now have loosened and allowed applied enough heat to give the molecules here enough kinetic energy to sort of wiggle and jiggle and loosen their intermolecular forces. That's right around our liquid, right above the freezing temperature. But we can apply more heat, and if we continue to apply heat, we can completely break the IMFs that hold the water molecules together. So we can break the LDFs, the dipole-dipole forces, and the hydrogen bonding that is present in liquid and solid water, completely separate the water molecules, and make them into gas. All right, so that's our states of matter. And of course, we can go backwards as well. We can take a gas and cool it down. And as we cool it, the molecules slow down. They have less kinetic energy. So they start condensing, and the attractive forces pull them together. And then if we continue to cool, we can go back to a solid. The only temperature where there is no more kinetic energy is 0 Kelvin. But it is not possible to reach 0 Kelvin on Earth. Not possible physically. Theoretically, 0 Kelvin does exist. The other thing is these two phases, the solid and liquid phases, are called the condensed phases because they are held together with forces and they are condensed. All right, so going back to our Pear Deck class slides. So what is pressure? Pressure is caused by collisions, molecules colliding. So you need two things. You need molecules and you need collisions. Okay, collisions between the molecules or with the surfaces of a container or any surface at all. Pressure is caused by collisions. The number of collisions, the more often things collide, the more pressure there is. And then the more force that they hit each other or a surface with increases the pressure. So collisions cause pressure. So we then went through a Pear Deck where we looked at several just gas law relationship questions. And so I'll run through these with you. The pressure of the gas in the container on the right would be blank the pressure of the gas in the container on the left. The answer is we have 3 particles here and 4 particles here. We have to say that the pressure is lower than. Less particles will create less collisions and less pressure. Here we have 4 atomic particles, 4 atoms, versus 4 diatomic molecules. What would the pressure be on the right compared to the pressure of the container on the left? Here it is the same. Even though we have 2 different sets of substances here, one with twice the mass of these particles, the pressure is going to be exactly the same. We are calling these ideal gases. Only the number of particles is going to affect the pressure. There are no attractive or repulsive forces between these particles. So the pressure is exactly the same as whether you have a gas with 1 atom, gas with 2 atoms, a gas with 3 atoms. Okay, only the number of moles, the number of particles will affect the pressure. Here we have, again, these lines indicate a faster speed for these particles. Well, we have same particles, one's at 10 degrees C, the other's at 50 degrees C. Okay, the ones on the right are moving faster. Okay, the pressure is going to be higher, right? If they move faster, they will hit each other and the sides of the container more often, and they will hit with more force. Next question is the relationship between moles and volume. So if pressure and temperature are constant, how are moles of gas and volume of the container related? Well, if we put in more moles of gas, the volume will increase if our pressure and temperature are being held constant. Here, this first flask has gas inside, and then we push down on the piston here with this syringe, and the syringe has gas in it. So we push down, and more gas goes into the flask. And ask, what does the pressure gauge read over here in the second picture? So it starts off at 5. If we put more gas in, will it go to 2, 5, or 8? It will increase to 8, right? If we put in more molecules, we create more collisions among the molecules. That creates more pressure. Here we have 2 cylinders with pistons. This piston is movable, but the piston on the right is being heated with a Bunsen burner. And they're asking, will this piston be higher than, lower than, or the same as this piston on the left? And since this is being heated, the piston is going to raise up and be higher than the piston on the left because we're heating these molecules. They're gaining kinetic energy. They start moving faster. They have more collisions with the walls, with the piston here. More pressure means it will lift this piston up. Here, the volume of the cylinder is halved. So we go from this volume to half the volume. On the right, the pressure would be blank the pressure on the left. Again, the pressure is higher. If we compress this volume and make it smaller, that's essentially increasing the number of collisions. They have less room to move, so they will collide more often. The pressure will go up. How much will it go up? So if the volume is halved, how much higher would the pressure be afterwards? If it was 5 atm before, atm is a pressure unit, what is the pressure afterwards? So if the volume goes down by 2, if you decrease the volume in half, the pressure does the opposite. It increases, it doubles, because you decrease the volume by a half. So therefore, afterwards, right, the pressure is going to double. Okay, so if it was 5 before, it is now 10 atm. Here, this is related to another question that we already did, but if we heat up these 4 gas molecules compared to these, the pressure on the right will be higher than the pressure on the left. Okay, so if we put all of these relationships together, let's summarize the relationships first. So, a summary of the relationships. We have P proportional to T. That assumes constant V and N. We have P proportional to N, constant N and V. Sorry, constant T and V. We have volume proportional to T, constant P and N. And then finally, we have P proportional to the inverse of V. This is at constant T and N. So if we put all these relationships together, we end up with PV equals nRT. All of these things are proportional to a constant, R, the universal gas constant. I will show you the units in a second. Here, the combined gas law takes, this is when changes occur in properties. So if we change P, V, N, or T, then we can use the combined gas law. So units for gas laws. First of all, the universal gas constant has these units. Okay, liters, atmosphere, mole, Kelvin. If you don't have these units for PV, N, and T, then you need to convert them. Okay, P stands for pressure. Here are the different units. Okay, 1 atm, 760 torr is the same as 760 millimeters of mercury, 14.7 psi, 101 and 101,325 pascals. These are all pressure units, and you need to convert if you're not given pressure units in ATM. Volume is in liters, milliliters, centimeter cubed. You could have meters cubed, right? You could have centiliters. Important thing is to convert into liters. Temperature. This is really important. Temperature must be in Kelvin. Has to be in Kelvin. The ideal gas law and all the gas laws depend on the Kelvin temperature. And then finally, N is the moles of gas, which of course is the same as the particles of gas. We can convert moles to particles using Avogadro's number. This is also the same as mass, right? Because we can convert moles to mass using the molar mass. So that's PV equals nRT in a nutshell. And a couple of qualitative examples. So here, if we have this example, and these you do not need a calculator for. You should be able to do these in your head. So if we look at example 1, we have 0.5 liters of gas in a syringe in a 50-degree water bath with a pressure of 200 millimeters of mercury. The syringe is compressed to 0.1 liters. So it goes from 0.5 liters to 0.1 liters. Held at 50 degrees C, constant temperature here. And then they ask, what will the new pressure be? So if we go from 0.5 liters to 0.1 liters, and we're at constant temperature, so that can cancel out. We have constant moles, no gases escaping from the cylinder. We now have just our PV gas law relationship. And on the next slide, I'll show you the answer. In example 2, 2 liters of oxygen gas in a sealed rigid metal cylinder is at 0.8 atm at 25 degrees C. To what temperature in Celsius should the gas be changed to reduce the pressure to 0.2 atmosphere? So we're going from 0.8 down to 0.2. So the pressure is going down 4 times. So we are holding the volume constant. We are holding the moles constant. So we just have a pressure-temperature relationship. But we need to be careful with that second one. Here, if we are going from 0.5 down to 0.1 liters, the pressure should go up by 5. So 200 times 5 gives us 1,000 millimeters of mercury. On the second example, the reason why I say to be careful is that here the pressure is going down by 4. So we should expect that if we change the temperature down by 4, we should get the pressure down by 4. Okay, but look here, we can't do that to Celsius because gas laws depend on the absolute temperature. So we have to get it down to minus 200 degrees C. Let's take a look here at a different example. So if we double the temperature, it does not double the pressure as you expect, right? Here, if we start at 1 atm and then we double the temperature, we are not going to get 2 atm of pressure. We only get 1.2 atm. Why is this? Because we are depending on the Kelvin temperature. If we want to double the pressure, okay, we must double the Kelvin temperature. So if we start at 50 degrees C at 323 Kelvin, I believe that's what this is supposed to be. It's supposed to be at 50 degrees C, and this is supposed to be at 100 degrees C, right? We have to go from 323 Kelvin and double that to 646 Kelvin, which is 373 degrees Celsius. Okay, so just keep in mind, gas laws depend on the Kelvin temperature. Okay, so that's where we stopped. And if you have any questions on these gas laws, we're going to be working on problems on Thursday, as well as looking at our Maxwell Boltzmann distribution and partial pressures. So lots of good stuff in gases. And so if you have any questions after watching this video, please let me know.